So let's consider the function f of x squared y squared. Find all relative extrema and saddle points, well, whatever corresponds. All right. So let's find the first partial, which in this case, well, the first partial with respect to x, that's going to be 2x y squared, and the first partial with respect to y, that's going to be 2x squared y, because the derivative of x squared is 2x, well, times that constant, and same for the y squared. Okay, so to get the critical values, so we need to set this quantity equal to 0, that is 2x y squared equals to 0. Well, divide both sides by 2. This is x y squared equals to 0. Well, using the zero product property, in this case we happen to have different variables multiplying, yielding a product of a 0. So this happens when, well, in one case, when x, so x equals to 0, let me do it here, x equals to 0, and y squared equals to 0, which is y equal to 0. Well, but this is kind of weird, because how are we going to represent these critical values? Well, if we go back to this point, to these points over here, and plugging for, well, if we try to solve for x, well, we won't be able to solve for x at all or for y at all. So that means that, okay, let's do one case at a time. The case x, if x equals to 0, but y can be any number, whatever that number is, or y equals to 0, we can have any number a for the value of x, because ultimately we will be multiplying these two. So x can be something and y equals 0, we can get that value equal to 0, that product equal to 0. Or on the other hand, b can be 0 times a 0 according to this equation. Well, that's still going to give us a product of 0. So that these points I'm going to look in general like this. So let's find the second partial derivatives. F of x, y, and fxy. So the derivative with respect, the second partial with respect x, that's going to be 2y squared. The second partial with respect y, that's 2x squared. And in this case, the second partial first with x and then with respect to y, that's 4xy. All right. So let's list the critical values here. So, well, we already have the critical points. Let's do fxx, fx, so fyy, and fxy. And let's get the values of d for each case. So fxx evaluated at the point 0b. Well, in this case, that's going to give us 2b squared. And fyy evaluated at, well, in this case, x equals to 0, that's 0. And in this case, evaluate the point for 0b. Isn't that going to be 0? So, in this case, 2b squared times 0, that's going to be 0. And then subtract 0, isn't it 0? Well, what's the conclusion when we get the d value equal to 0?
Saddle point.
Not saddle point. Inconclusive, right? Let's have a look at this point right here. So, plugging in a comma 0 on the second derivative with respect to x, well, only y equals to 0, that's 0, and then that's 2a squared, and that this is also 0. Doing again the d quantity, it's also giving us a 0. So this means inconclusive. So, well, how about we have a picture of this? Well, so because that's kind of a weird example, that's kind of a weird surface, and the way we're treating these points 0b and a comma 0, what do they mean? So that means b can be anything. For example, the point 0 1, 0 1, 0 2, 1 0, 2 0, 5 0, 0 5, etc. These points are gonna lie exactly on the corresponding x and y axis. Well, so let me pause the video. Let's continue with word problems, optimization problems. Remember finding the dimensions of maximum area, of maximum volume, or we have this volume. We need to find the dimensions that would give us the least amount of material to wrap a gift. That's the surface area. We want to minimize the surface area subject to certain volume, or we want to have the maximum volume given some information. So the usual, what are the steps to solve max and min problems? Always, whenever possible, by the way, draw a picture so we can see what the situation is, so we can label our given information in the problem, and then write down the function, the mathematical model that first comes to our minds. In some cases it's going to be very explicit, volume, or something like area. Okay, so we would be thinking of that area or volume of that geometric shape that we're dealing with. Well, in the case that it's a geometry application. And just the same way we did back in Calculus 1, we always set the primary equation, which is the objective function, the one that we do calculus on, take the derivative, set it equal to 0 to find critical values. And we always had this secondary piece of information, which in this case is the constraint, right? And that information is going to help us reduce the amount of variables. Because, for example, back in Calculus 1, when we were dealing with an area problem, so we had this area of xy, which is simply xy for a rectangle. But in this case, that was Calculus 1. In Calculus 1, we were not supposed to work with two variables, so we used some information, maybe the perimeter, and solve for one of the variables, plugging in the objective function to reduce it into a function of only one variable, and then do the calculus. We're going to do something similar over here, because we are going to end up with functions this time of 3 variables. So we need a constraint or a secondary equation to eliminate one of the variables and work with functions of only 2 variables. All right. So what do we have? A company is designing a rectangular box with no top and a partition down the middle. The box must have a volume of 48 cubic inches. Find the dimensions that will minimize the amount of material used to construct the box. Well, in this case, that amount of material to construct the box, usually it's not very clear about what we're going to use in this case, and that happens to be the surface area. And in this case, they're telling us the maximum the volume that we are required to have for that box. So number 1, let's draw a box. So let's draw a rectangular box. However, they're also telling us that we want a middle section. So it's going to be important to take it into consideration when we set up the problem. All right, so we have a constraint, number 1. So, number 1, we have let's write down the objective function. The objective function, it's going to be f of x, y, z equals to number 1. So we need to define the different dimensions of the box. So let's call this X, the whole thing, Y, and Z. So in this case, this box will be formed by a bottom, only one, well, it's the bottom, but if we had a top, that'll be 2 times the same dimension. So for the bottom, the area for the bottom is XY, and plus, what about front and back? So front and back involve multiplying X times Z, all right? X times Z, but in this case we're going to multiply this by 2 because it's one rectangle for the front and another rectangle for the back. Now, what about the sides? For the sides, we need to multiply Y times Z. However, it's not going to be just 2 of them the same way from the front and the back, because notice we have this middle section in this case, right? So we need to multiply that by 3. And that's a 3YZ, all right? In this case, well, how about we label? Bottom, sides, no, front and back, and sides. Oh, come on. Sides plus middle partition. So if this box had a top, then we would have multiplied this by 2, because it would be the same quantity that involved the top and the bottom. But in this case, it's open. It's an open box, right? All right, so here is a problem. So we have too many variables. We need to get rid of one of the variables, and we can do that by using this piece of information. They're giving us the volume. So let's label this as our objective. Objective function. And let's label this too as a constraint. Okay, so they're telling us that the volume, which is given by the product X, Y, and Z, because the volume of a rectangular box is the length times the width times the height, which in this case is X, are labeled by X, Y, and Z. So, but in this case, we're given the numerical value of the volume, which is 48. So we're going to use this second equation to solve for one of the variables, and whatever we get, we will plug in the objective function. This way we will get only a 2-variable function. Well, so back in Calc 1, we usually used to solve for y so we can work with a function of x, and in most of the times we work with functions of x, y, and in this case I would like to work with a function of x and y. So I think it would be a good idea if we solve for z in this case. So what are we going to do once we solve for z? We're going to substitute this z equals to 48 over y. Let me do another one. Oh, come on. We're going to substitute here and here. So this will turn our f of x, y, and z into an f of x, y. So that's xy plus 2 times x times z, which is 48, over xy, plus 3 times, or 3y, rather, 3y times 48 over xy. And in this case, well, we can do some cancellation, some simplification of multiplication of numbers. So after simplifying all this, we should get f of x y equals x y. Cancel the x's, multiply 2 times 48, that's a 96 over y, plus 3 times 48, that's 144 over x. So that's the objective function simplified down to two variables only. So this is the function we will do calculus on. Alright? So, well, in this case, lucky for us, we won't have to do the d-test because they're already telling us that this is a minimum, so we won't have to do all that. So all we have to do is find the derivatives, set it equal to 0 to get the critical values, and just answer the question. Alright, so let's find the first partial with respect to x. So, number one, I would need to rewrite this function as xy plus 96, y to the negative 1, plus 144, x to the negative 1. So taking the partial with respect to x, the first term is y minus 96, y to the 144 first, 144 x to the negative 2. The first partial with respect to y will be, for the first term is x, and then minus 96 x, or y rather, y to the negative 2. So those are the first derivatives. Well, we don't like this with negative exponents, so let's write them down as positive exponents. So that's y minus 144 over x squared, set it equal to 0. Well, I'm going to do this, the setting on the side. So, and that's x minus 96 over y squared. Okay? So we have to solve this equation for x and y. So we need to find a way. So number one, y equals negative, y minus 144 over x squared on the one hand equals to 0, and x minus 96 over y squared equals to 0. So we need to solve for y over here, 144 over x squared, and x equals to 96 over y squared. So we need to find a way to solve this equation. So the way I'm going to go about it, I'm going to substitute this 144 over x, which is equal to y. I'm going to substitute it here to get an equation that depends only on x. So this means x, or 96 over 144 over x squared, quantity squared. Alright? And yes, this number is going to get a little crazy. So number one, so this will be, in the first place, move it here instead. So it looks like I'm solving an equation. So I'm going to square numerator and denominator on the quantity in the denominator. That's, for now, let's call it 144 squared. Let's not square the number to get a big number. It's really going to be a big number. And that's x squared quantity squared, that's x to the fourth. So in this case, well, dividing by a fraction is the same as multiplying by the reciprocal. So this will be x equals to 96 times x to the fourth over 144 to the second power. All right, so let's solve this equation. So number one, let me just call it x equals to 96 x to the fourth over 144 squared. I'm going to have all terms on the left hand side. X minus 96 x to the fourth over 144 squared equals to 0. So we can solve this equation by factoring. Well, because we have the common factor of x. So that's 1 minus 96 x to the third over 144 equals to 0. Well, so if we solve this equation for x using the zero product property, number one, this equation equals to 0 if either x equals to 0 or this quantity equals to 0. But the thing here is, would it make sense to consider the solution x equals to 0? I mean, what would be the volume of a box whose length is 0? Well, there's no box, right? So here is where we consider those, contextual ideas. So in that case, even though it's in the domain of the mathematical function and all that, but in this case, well, there's no box with a length equals to 0. So in this case, 1 minus 96 x cubed over 144 squared, let's keep solving this equation, equals to 0. So that's 96 x cubed over 144 squared equals to 1. X cubed equals 144 squared over 96, and taking the cube root, that should give us x equals to 6. All right. Well, I have it on the notes as x equals to 6, but if you want me to verify that, how about we do it on the graphing calculator? All right. So let me go back to the recording. So we got the solution for x, and again, we don't have to do the d-test. All we have to do is just back substitute x equals to 6 in our equation that depends on, to find the y right here to get the x. So let me call this a solution. Let me label over here. So that's y equals 144 over 6 squared, which is 36. That's y equals to 4. 144 over 36, that's equals to 4. And further back, let's go back to our constraint equation. In this case, that's z equals to 48 over x times y, the values that we just found. That's a 6 and 4, and that should give us z of, I have a 2. All right. I know the numbers are like all over the place. I'm going to answer the question right next to the box. Well, we're done with the math. In this case, we're done with the math. Now we need to answer the question. So the question is, what are the dimensions? So x equals to 4, y equals to, oh wait, it's x equals to 6, not 4, y equals to 4, and z equals to 2. In other words, in this case, what is it? In inches, so that's a 6 inches by 4 inches by 2 inches. So these are the dimensions that give us that volume of 48 cubic inches, and in this case we require the least amount of material to construct that box. All right, let's look at another example. The next example, it's an application to biology. So it's the Hardy Weinberg Law. Common blood types are determined genetically by 3 alleles or alleles, A, B, and O. A person whose blood type is AA, BB, or OO is homozygous. A person whose blood type is combined AB, AO, or BO is heterozygous. The Hardy Weinberg Law states that the proportion P of heterozygous individuals in any given population is modeled by this model 2pq, 2pr, 2qr, where p, q, and r are going to be the percent of allele A in the population. Q represents the percent of allele. It's supposed to be B, I think, in this case, and R represent the allele O in this case. Now we need to use as our constraint. We need to use the fact that P plus Q plus R equals to 1. Well, where did we get that information? Even if we were not given that information, well, since in this case we're talking about proportions, so if we express proportions as fractions or decimals, the total amount has to add up to 1. Just like in percentages, everything has to add up to 100, right? So that's what this P plus Q plus R equals to 1, all right? So we're going to use this constraint to show that the maximum, again, they're telling us that it is a maximum, no need to do the D-test. Proportion of heterozygous individuals in any population is 2/3. All right, so let's use our objective function. So that's P of PQR. That's 2PQ plus 2PR plus 2QR. All right, and so that's our objective function. And our constraint, this will be P plus Q plus R equals to 1. You know, all the proportions have to add up to 1. So, okay, that's 2. So, okay, so in this case, we have a 3-variable function. We need to eliminate one of the variables so we can have only a 2-variable function. So, I'm going to solve for R over here. That's 1 minus P minus Q. And we're going to substitute this constraint here where we have the R's. Okay. So, that's going to become P of PQ now, not PQ and R. 2PQ plus 2PR, but R in this case is 1 minus P minus Q plus 2 times Q times R, which is 1 minus P minus Q. Alright, so yeah, we'll have to do this distribution. Hopefully it doesn't take too long. And so that's going to be 2PQ plus 2P minus 2P times P, that's 2P squared minus 2PQ. Good news, check. We can already cancel the first term with that term, and then plus 2Q minus 2PQ and minus 2Q squared. All right, so we're going to be left with a function, well, actually 2p with, no, that's the only, those are the only p, that's fine. So we're going to be left with negative 2p squared minus 2 or plus 2p minus 2q squared plus 2q minus 2pq. So what I'm doing is writing it in descending order of powers and also alphabetic order, so it's easy to manage this function. So P, Q here. So let's find the partial derivatives. So in this case, well, it's not going to be P, f sub x or f sub y. It's P subscript little p. This subscript means that we're finding the partial derivative of the big P function with respect to P in this case. So that's going to be negative 4P plus 2 and 0, 0. And the derivative of this last term with respect to P, isn't that going to be negative 2Q? All right. I know it's different letters than we're used to, X, Y, and Z, so you guys following me here anyway? Alright, so let's do the partial with respect. Q. Alright, 0 for the first term, 0 for the second term, negative 2Q. Negative 2Q in this case, plus 2.
Wouldn't it be negative 4Q?
Oh yeah, negative 4, that's what I meant. Well, not what I said, right? So, and minus 2p, right? So, these two partial derivatives, we're going to set them equal to 0, and because we have all variables on both equation, most likely we will have to solve a system of equation. Well, in fact, it's always the case. So, in this case, negative 4p plus 2 minus 2q equals to 0. In this case, negative 4q plus 2 minus 2p equals to 0. So, how about we leave all the variable terms on the left hand side of the equation and the constants on the right hand side. So that's negative 4p minus 2p, minus 2q equals negative 2 and negative 4q minus 2p. Well, actually, I'm going to write this in reverse order so we have this in the alphabetic order so we don't get confused when solving the when we try to solve the system of equation. And equals to negative 2. But did you see that we can get rid of all these negatives? Because it's all negatives on both sides. So let's erase the negative sides, the negative signs on the first terms, change that to a plus, and erase this other negative. So this is the system of equations that we will have to solve. And well, you know, a bunch of methods to solve systems of equations: elimination, substitution, matrices on the calculator, matrices by hand for those of you who are in linear algebra. Alright, using the Gauss-Jordan elimination method. But to save some time, I'm going to give you the result. P equals to 1/3 and Q equals to 1/3 as well. And so those are going to be the values P and Q that will give us that the maximum proportion of heterozygous individuals in any population is 2/3. What do we need to do in this case? We need to go back to the original function, PQR. Oh, number one, we first need to solve to obtain the value of R, right? So that's 1 minus 1/3 minus 1/3. Well, what's that? 1/3, right? Yes. So let me box them. So we need to find P of 1/2. 1/3, 1/3, 1/3. So that is 2PQ, which is 2 times 1/3 times 1/3, plus 2 PR. Well, surprise, 1/3, 1/3, plus 2, 1/3, 1/3. Well, so what's 1/3 times 1/3? Isn't it that 1/9 times 2? So that's 2 9s. But that 3 times, so that's 6/9, isn't it? That adds up to 6/9, which reduces to 2/3, which indeed is the result that they were asking us to prove in this case. All right.